Well, first, thanks organizers for this opportunity and for organizing this wonderful workshop. I've been really enjoying the talks and the discussion with a lot of friends. I think for this audience, I don't need to explain why conformal field theory is important. And I think probably many of us have a dream to classify all possible conformal field theories. And we last week we heard a beautiful talk by Braden, who explained how to classify two-dimensional conformal field series, rational ones with like up to 4 characters. We the reason that 2D is successful is because well, it has a lot of much more interesting mathematical structure, and this powerful mathematical structure makes it working. I want to tell you a story about the classification of conformal fixed points in a different limit, which is the more old-fashioned formalization expansion limit. And I mean, we do what we can do, right? So I think you might be surprised that even in this limit, to classify the fixed point is still a non-trivial business. It takes a lot of energy. I will explain 2 approaches. The first approach is a kind of more brute force approach, and which is based on this question asked by Slava, answered by Robert Bryant on mass exchange. I mean, you can search for this question, which is a quadratic ON invariant equation for 4 index tensors. Just search for it. There's a very good answer given by Robert. The second approach is more group theory, which I will explain. But to set the stage, let me just explain the problem we will consider. We will focus on orientation on scalar fields. And basically, we are going to consider the Lagrangian of this form, the one that Stefanos just wrote down. So. We assume that we tuned all the other couplings to 0, the phi squared terms and phi cubed terms. We assume that it has been tuned to 0. And we take this lambda to be absolutely arbitrary. So if this lambda coupling is equal to dirt Ig, dirt KL plus permutations, this would be the more familiar ON invariant theory that people have considered. And we are going to take this lambda to be arbitrary and to see what kind of fixed point we are going to find. So the beta function, if you do the calculation, looks like this. The leading piece comes because you are doing this in formalization dimension. The lambda phi 4 term is slightly irrelevant, so you have this contribution. The subleading terms come from the Feynman diagrams, the first 2 loop Feynman diagrams, which essentially looks like this. You have I, G, M, N, K, L here, plus permutation. Okay? So this is just the very innocent 1-loop beta function. And to search for fixed points, mathematically, we just want to search for solutions of this equation. We set it to equal to 0, and whenever we find a fixed point, whenever we find a solution to this equation, it would be a candidate. Well, it would be a conformal field theory in formalization expansion. And we will worry about how to continue to actual physical 3-dimension later. But if you look at this equation, this is basically just a polynomial equation, right? So, yeah. maybe this, right? Yeah, thank you. Yeah, so this is the polynomial equation. Let's do some counting. The number of variables is equal to n plus 1, n plus 2, n plus 3 divided by 4 factorial. When n, let's see, equal to 3, this gives us 15. So it's a polynomial equation. It's quadratic, very low degree, but still, I mean, there are a lot of variables to solve this equation completely. To find the solutions, to classify the solution space of these equations is a very non-trivial business, in fact. So, I'm sorry, I didn't mention that this indices RGK runs from 1 to n. And n for me is counting the number of scalars, basically. So let's see. I mean, this equation enjoys a rotation symmetry, right? If you all go to R, I prime, G prime, K prime, L prime. After this rotation, since the right-hand side is 0, this equation is still satisfied. So whenever you find a solution, you apply an ON rotation, you are going to generate another new solution. So this would be so the solutions would be like not discrete. It will be forming some manifold. So we have to fix this gauge. So just to explain how it's done. We're going to first decompose this guy into ON representations. This is a singlet representation of ON. This is symmetric traceless tensor, rank 2 representation, and this is rank 4 symmetric traceless tensor representation. And the gauge fixation, we can pick any of your favorite, but a convenient one is basically setting IG less than, well, equal to T hat G I for I less than G. Okay. If you do the counting, these are some extra constraints, which gives you n times n minus 1 divided by 2. This will be the number of generators of ON. So you expect that after this gauge fixing, you fix all the degree of freedom left over in this ON rotation. So in fact, after this, we can basically brute force do it, meaning that, okay, now we have a parameterization of our tensors. We have this as an unknown variable. We have this one, which is a rank 2 tensor. You just want to parameterize it and make sure that it's symmetric traceless. Also similarly here, you make sure it's symmetric traceless, but also satisfy these constraints. This would be a set of polynomial variables. You plug it back into this equation. In Mathematica, you hit Shift and Enter, and you try. So for NQ2, I didn't actually try it. Well, no, at some point I tried it, but immediately it pops up the answer. Actually, I mean, because NQ2 is very simple, you don't really need to use Mathematica. It's not very hard to convince yourself that the solution generated by Mathematica is a complete solution. You can even maybe do it by hand. So this was reported in one of the paper by Stergel and Hugh Osman, and all the solutions has been present there. So for encode 3, you had to wait much longer and be patient. Maybe after 1 hour, depends on how good is your computer, you will notice that Mathematica finally gives you an answer. But the real question is, should we trust it? How to convince ourselves that this is the full list of solutions? Usually Mathematica is good, but we want to understand whether it's complete set or not. For encode 2, how many solutions are there? Sorry, I don't know. Okay. I mean, the ON, the O2 one, but the decoupled ethane is also there,
Yeah, yeah. Decoupled
right?
don't count.
Yeah. But also, yeah,
The only
maybe this
solution is
too, right?
O2. That's it. The only fully interacting solution is O2.
Okay, yeah. The only for interacting solution is the O2. But this one has much more structure. And so, so the algorithm behind the mathematical approach is really the approach called Grosvenor bases. And I should see that there's a very good book by Cox, Leto, and O'Shea, which basically is called Ideals, Varieties, and algorithms. It's a graduate level textbook to mathematics. And what it really do for you, well, let me first explain what ideals are. I mean, it might sound terrifying, but it's really nothing special. So ideals is a subset of this means the space of all polynomials with n variables, x1 to xn. And ideal is a subset of these polynomials satisfy these three conditions. One is like 0 belongs to this ideal. 2 is like if f and g belong to this ideal, then f plus g belong to this ideal. The third one is that if f belongs to this ideal and g, let's see, h belongs to this polynomial R, any arbitrary polynomial, then f times h belongs to this ideal. Okay? Why is this the same question we are studying, you solving polynomial equations? If we have a set of polynomial equations, f1, f2, fn, we want it to be equal to 0. Of course, if f is one of these equations, g is one of these equations, the summation of them is one of these equations, it is still 0, right? So this ideal means the space of polynomials that vanish on the same set, which on the set of solutions of this set of equations, right? So it forms an ideal. So if f belongs to I, means f is 0, then you multiply it by some arbitrary polynomial, it's still 0, right? So this is why this is related to us. And the mathematical concept of Grosvenor basis is really just a good generating set of these ideals. So this would be a generating set of this ideal. You start from this, you do any of these operations, you generate all the polynomials in this ideal. But there are better sets, right, which people call Grosvenor basis, which is actually a bad name, but should really be called a generating set. But it satisfies a lot of nice properties. And before explaining the Grosvenor basis, let me explain something called the monomial order. So if I have x1 to the alpha 1, xn to the alpha n, I want to be able to compare different monomials to see which one is higher order, which one is lower order. So as you can see, my alpha is some vector in this vector space. So I will define some order called lexicographic order. As long for two monomials given by alpha and beta, I define alpha is bigger than in lexicographic order than beta, as long as the leftmost entry of alpha minus beta is positive. Okay? So the takeaway message, this is not a course on nonlinear algebra. The takeaway message is that you start from some initial generating set, you specify some monomial order, let's see, lexicographic order, you ask Mathematica to do the calculation. In the end, Mathematica will be able to generate for you a set called Gordon basis, which is a set specific to this monomial order, okay? And everything is mathematically well defined. That's the takeaway message. So the reason that we pick this lexicographic order is because in the end, our equations would be in a really nice shape. Suppose you start from our original equation, and you do this procedure. In the end, you are going to get a set of equations which looks like this: T1, 1, 1, 1, all the variables, S, a huge number of generating set. But the second one would just be T1, let's see, T111, T1112, blah, 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 blah. The second one, however, would be eliminating the first variable already. Okay? And you keep going, maybe it's 2. I don't know what this number is, but in the end, in this so-called Gordon basis, you will get a polynomial set, which is in this form. This is upper triangular form. The first equation involves all the variables. The second one, you eliminated already the first variable. The third one, you eliminate further 2 variables, maybe not the third one, but up to some number, you get some equation. The equations below involves a smaller set of variables, okay? So if your equations are good enough, in the end, the last equation you are getting will be the equation involving this S variable alone, okay? And S, if I remind you, my lambda was parameterized in this way. And this S is the isotropic piece of my variables. So you do this in Mathematica, in the end, you are getting this equation. This is a huge set of equations. It's very long, but it captures all the solutions we know about. And let me just comment by saying...
Can I ask you a question?
Go ahead.
Are the F1, F2, and so on linear in T, in the T's, or...?
No, they are very nonlinear equations. Well, for S, they are...
So for any given S, you can have more than one solution if it's nonlinear in the T's, right?
Well, in general, it's possible, but in this case, I don't think we encountered that. So I didn't really check the F1, what does it look like. It's a really long equation. But for us, I think, in our case, I think each S, you have just one equation, I understand. I'm just saying, for a generic set of equations, for each S, you can have many equations. But for us, after we do the analysis, we realize that for each S, for our case, there's just one equation, which is probably because we have a good parameterization or not. No, each S, we have one solution. Well, each of these fixed S, I mean...
If it's nonlinear in T, how is it?
Yes, it's going to appear 30 times, but it will manifest itself in different...
So your claim is that every S leads to a unique solution?
Let me finish this part, and you can ask me again. So for each of these S, they correspond to a set of equations of this set of equations, right? But in the end, because we already did the gauge fixing, we are losing some freedom in rotating these solutions. Therefore, an equivalent solution can appear many times. Okay, So this one, you would get the free theory, for example. This one, you would get the decoupled Eaton theory. This one, I think it's the potential looks like phi 1 to the fourth, 1/3, plus phi 2 to the fourth, 1/3. So you can see this solution is a decoupled, well, two Eaton, and a free theory. The third one is a free theory. So this is solution. But this solution appears 30 times, right? So whenever, the reason that this form is especially interesting is because I can first solve this one with using my techniques to solve like one variable polynomial equations. And then I can plug back to solve the second variable, and then plug back to solve the third variable, and so on, right? So this gives me a systematic way of finding out the solution of this system. So what I'm claiming here is that for fixed S, even though in this sets it appears many, many times, but in the end, you realize after some O3 rotation, you realize it can all be rotated back to this one. Yeah.
Maybe in this case, but in general, you haven't proven that that's how it works.
Yeah,
if it's nonlinear in the T's, you go up, and you'll get many solutions for the T's, and you have no idea if they might be rotated to.
Okay, let me see what I did. What are the checks I did? I checked all the. I checked the
checks,
first.
The checks might work, but
yeah.
Strictly speaking, it doesn't follow what you're saying. The checks might, you know.
Yes. So this is an observation for this subsystem.
Okay.
Yeah. Thank you. So we have a systematic way of solving this set of equations, and this was basically done by Robert in response to Slava's question in that mass exchange. So, I mean, the obvious thing to do is to push it to higher number of scalars instead of restricting yourself to equals 3. So we started to do this, find some parameterization, try to run it on some fairly big workstation. And the conclusion is that we didn't solve it. And the reason, I think, is related to the comment I mentioned earlier. So for each of these solutions, even though, I mean, in a good basis, it looks like this, but in this Grobner basis, it appears many times. So this polynomials becomes a really high degree. And I mean, at some point, so basically what happens is that you use the state-of-art Grobner basis algorithm recently posted by some, well, I'm sorry, I forgot their name, but the software is called MSolve. You can search it online. You run it on some workstation, and after a few hours, the code starts to take up all the memory, and later it's queued by the system. So it never outputs anything. I think the reason is really related to the fact that these degrees are really high, and it's really hard. Well, it's not very. We are not very sure about how to proceed. Well, one thing you can do is to impose some extra symmetry. For example, you impose some extra symmetry like phi 1 go to minus phi 1 to be preserved, and you would reduce the number of variables in your system. This would be a subset of solutions to the original solution we care about. I mean, after imposing like maybe 2 Z2 symmetries, the system becomes solvable. And we checked the solutions we found, and 9 of them are the new solutions. So we haven't found any new solutions, and we haven't finished classifying this encode 4 system. That's the, go ahead. Yes. I use my rotational. Sorry.
Can you repeat the question?
There are some confusions about how why I can get many solutions instead of one after I used the ON rotation. So I use this ON rotation, but it only but it's strictly speaking it only fix the continuous rotation away from some fixed point, right? You pick a locational point, you restrict, you didn't fix discrete elements. Yeah, so your discrete elements would generate new solutions. It's a bit more complicated than that, but yes, that's essentially the story. So yeah, so this is the state of art for the moment, and the upshot is that Angle 3 has been done, and Angle 4 has not been done. And feel free to think about how to do it. The second way we are going to talk about is a more group theory approach. So, of course, we saw that to brute force solve the Angle 4 problem is hard. But suppose we are interested in, we are going to introduce a subset of the system, so which is the physically, I would argue, more interesting systems. So my Lagrangian, I wrote already, but let me see. Suppose I have a Lagrangian, I fix a group, a symmetry group of your system. I can write down my Landau actions according to this symmetry group. So I would have some invariant polynomials, maybe AI,
So you may summarize for n equal 3, then the situation is what exactly? It's known, right?
Okay. Let me summarize. The Angle 3, I mean, this algorithm gives you all the solutions, and no new solution was discovered. The last, well, I mean, we know what each one, what solution each of these S corresponds to. The last one that has been discovered is this one. You can see that it corresponds to some irrational number for S. Okay.
I mean, that's known for a long time. It's not.
Well, no, this one has
That's just
two or 3 years. No, this is a very new one. It was discovered by Codello.
No. This is a very old one. It's been discussed a long time ago.
I see. So maybe you know more about the reference.
It's just biconical with I2 and O2, with Ising and O2.
No, but
right?
the biconical one would have rational S. This is
no, it won't. It's biconical with Ising and O2, right?
I don't think so, but we can check later.
Isn't Slava biconical with Ising and O2?
I think the biconical corresponds to one of them here, which I don't remember. Biconical Ising and O2.
Yeah.
No, I think that one probably is somewhere in between. But we can check.
No, I'm pretty sure.
You're pretty sure?
Yeah.
Okay. Well, I mean, the last time I saw these solutions being discussed was in this paper. That's okay. No new. Well, all the solution has been known. This one is complex. You don't have real solutions. So, yeah. Okay. These are real. This one gives real solutions. This one gives complex solutions. So maybe that one is like. Okay. So now we switch to the group theory approach, and so fixing a symmetry group, you can write down the Landau series. This means degree 1 polynomial, degree 2 polynomial, degree 3 polynomial, degree 4 polynomial, and higher ones. But later we are going to do 6 minus 6 expansion. The higher ones would be irrelevant. The corrections will be small, so we don't care about that. We are going to impose 2 conditions. One condition is that there is a, well, the n-dimensional representation of On remains irreducible. Under this group G. Why do we want to impose that? Because if we impose that, we are going to kill these ones altogether. right? So the degree ones, because it's a reducible representation. You don't, if there's a single vector along some direction that is invariant under rotation of this group, you can put it in your Lagrangian, and that would be allowed. So if you require to be reducible, you kill this one. If you require to be reducible, you are left with one mass terms, which the mass terms, the second term, what you are getting is just m squared phi I, phi I. Okay. And this, well, we are going to talk about the conformal field theory later. So whenever we have more relevant terms, that means in reality of statistical physics systems, we have to do extra fine tuning to reach the fixed point. So these if the symmetry allow extra pieces here and here, this would be the tri-critical point, quadricritical point, and other fixed points. So we are going to restrict our attention to a subset of solutions satisfy this condition, which means we are restricting ourselves to the fixed points that are easier to access through experiment or lattice simulation or whatever. So the second condition you can already infer, we want to also to exclude this term, which is also what is called Landau condition. Okay, Landau condition basically tells us we don't want these phi cube terms, but there's another way to understand how Landau had his intuition. If you draw the potential, let's consider one single scalar for the moment. We draw something like a m squared plus phi to the third, phi to the fourth. The potential looks like this. This is your phi field. So you can see the potential has two minimums as you tune this A to make them be equal height. There's a barrier in between. So if you remember your statistical physics course, this means that there could be coexistence of two physics, right? One in here, one in here. And this would mean the phase transition is first order. And we don't want this. We want second order phase transition. And in other words, we want this guy to be automatically disallowed by the group theory. And that's the condition that not allowed. Symmetry. So as you can see, this is the subset of the solution set of that equation, which we would claim that it's more interesting physically because they are easier to access. So the approach we are going to take is to enumerate all the possible groups, subgroups of O(n). This may sound terrible, but actually the list is infinite. I mean, you may be familiar with, actually, the easiest way to think about it is that O2 has all the Zn cyclic groups embedded in it automatically. This list is infinite, right? So, but the problem is that after imposing this irreducibility condition for O5, well, sometimes the list is still not infinite, but for us, for the O5 case, we were going to care about the list is finite. But even if the list is not infinite, not finite, for example, O2, you have Zn embedded in it. I mean, all these are falls in the same class, and you can do it easily. So basically, by imposing these conditions, we greatly reduce the list, the cases we need to consider, and this become tactable using human labor. So let me give you a little bit background knowledge about what people know about the subgroups of O(n). So O3, the subgroup is the famous AD classification. This has been known since ancient Greek because they love Platonic solids, right? So O4, I mean, it's actually related to O3 because of the similarity of the algebra is like SU2 times SU2. But you have there is a very good book by, which I think was the one who first classified this. And O5 is much more recent, which is in a paper called Finite Groups Acting Homology by finite groups acting on homology for spheres and finite subgroups of SO5. You can find it in our paper, the reference. And O6 was known 100 years ago because of its relation to SU4. It's known in a famous work by So the intuition is that if the group is too small, there's no symmetric factor that can rotate from the first scalar to the last scalar, for example. I mean, this phi would become irreducible, and you just discard that case automatically. So our approach is actually based on a very famous paper, well, a very important paper by this is a very good paper which basically did the groundbreaking work for this approach. They worked on this O4 case, taking the mathematical literature available, and then started the irreducible fixed points in this case, in the N-4 case. A lot of, well, they really paved the way. And we did some modifications of this approach. And the most important modification we did is to use a software called GAP. Well, many more, but this is the most important one. Modern days, we can use computer. That's the point. At that point, they must have done everything using hand, and it's really surprising. It's really ahead of its time. But now GAP, a lot of group theory calculation, you can do it with one command, and that's pretty much, it becomes very, very easy. So GAP is a computer algebra computer software, which allows you to calculate things like character table of a group for finite groups, to find the subgroups of a finite group, find the maximal subgroup, or any of the subgroup. And I mean, you can find the representations of the discrete group in terms of matrices. And it has a lot of amazing applications. So let me remind you that later we are going to, let me see. We have a list of all finite subgroups, or, well, they did the O4 case, we're now going to do the O5. We have a list of all finite groups of O5. We want to find the irreducible ones. But we also want to find the group-subgroup relations between these groups.
So can I ask a question?
Go ahead.
In this work you mentioned by Codello for n equals 4, and also my work.
This is n equals 3. Sorry.
They also had some.
Yeah, they had some.
Well, not this. Yeah, they had some follow-up work for it, and also had some work with Hugh, where we found 3 more solutions for n equal 4 that were missed in that paper. 2 of them with discrete symmetry groups.
Okay, maybe
How did
yours was the last one. Yours was this 3?
Well, I think I know my papers, but anyway.
Yeah.
There were 2 solutions
Yeah.
that have discrete symmetry groups for n equals 4
Yeah.
that were somehow missed by this classification of the Brezan et al. Paper.
But are you sure they are like irreducible, meaning that they're just one mass term? The important thing is that we care about just one mass term. So basically, yeah. So so we need not only a list of irreducible groups, we also need their group subgroup relations. In the end, we are going to give a tree of groups. Well, not a tree, a graph, a directed graph. Suppose we are going to calculate the invariant polynomials of this series and then plug in this equation to calculate the beta functions. Suppose this guy has some invariant tensor. Let's see P1, P2. Let's say they are degree 4. And suppose this guy has some invariant tensor, which is P3, P4, P5. And because this guy is a subgroup of this guy, so these invariant polynomials would also be invariant under the action of this group. Suppose you choose the basis properly. And therefore, the conclusion is that all these invariant polynomials should be written as a linear combination of these ones, right? So this tells us, okay, we don't really need to consider all the Landau series. We just need to consider the smallest one. The smallest member in this directed graph. We focus on this one. As long as we do the beta function calculation, we will find all the fixed points with this symmetry and any higher symmetries. So this explains why we need a group-subgroup relations among them. And this greatly simplifies the amount of work we need to do in the last step, which is to analyze the Landau action and to search for fixed points. I want to show you, well, yeah, so let me again explain a little bit how we did the calculation. So we have a list which contains the maximal subgroups of this O5. We start from the maximal one. Actually, you start from arbitrary one. You use gap to find the irreducible, to find the subgroups. You find the maximal subgroups. Start from G0. Second step, you check irreducibility. Which is basically you calculate this quantity. This is the character of that representation. This is the conjugate of that character. This is the number of elements in that conjugate class. You are supposed to sum over all the conjugate class and divide it by order of the group. Okay? The claim is that this quantity is equal to 1 if your representation is irreducible. It equals to more than 1 if your representation is not irreducible. This is one thing. This is good. But there's another subtlety at some point. Suppose you repeat this step. You find two groups at level 4. You want to ask whether these two groups are the same or not, right? You want to be able to check whether they are the same. This turns out to be a subtle step. So the first thing you want to check is whether these two groups are isomorphic of each other or not. So, well, I mean, luckily that can be done easily in gap. You just build isotropy. If isotropy is yes, if you can build an isotropy, then these two groups are isotropic to each other. But, well, yeah, isomorphism. You build isomorphism. The second step is that you want to check whether they are the same representation or not. Okay, let me draw some graph. Let's see, G3, and I have a repetition which is row 3, which goes from the elements into a matrix. Okay, I have another group which is G4. I'll call the repetition G4, which is a map from G4 to some matrices. Now I already did the first step check. Now I can build an isomorphism between these two groups. So I have another representation of this, sorry, this G4. I have another representation of this G4, which is row 3 composition of this isotropic map. This, again, is a map from G4 to a matrix. So I want to be able to check whether these two representations are the same. Luckily, in GAP you can do it, because in GAP you can build this isomorphism, which is basically given as a map in their language. And then representation is given a map. You just compose this map, and you calculate the characters of this one and this one. You would be able to test whether they are the same representations or not. Okay? But if the answer is no, that doesn't necessarily mean that your two groups are different. Your matrix groups are different. So when I talk about subgroups of O5, I really mean a set of matrices which there forms a group, and that group is given by multiplication rows, right? But there is a concept which is called automorphism. It's a map from a group to itself, okay? So it may be possible that two representations, row 1 and row 2, they are both 5-dimensional, but it could be possible there's the automorphism that rotates, that maps this one to this one, maps two representations from one to another. Automorphism is an automorphism that maps group elements to itself, respecting the multiplication rows. So even though if two representations are different, in the representation theory sense, they might be related by automorphism. Remember, I said these groups are just a set of matrices. When I reshuffle these matrices, I'm not going to get a new group. I'm going to get the same group. So therefore, you have to take into account this automorphism, and this is the important starting point in our classification. And after taking this into account, you really have a list of all possible, a list of irreducible groups. And there's another quantity.
Can I ask a question?
Go ahead.
This is basically trying to find CFTs with the same symmetry group, but with different order parameters? Is this what?
No. We are trying to see, okay, as a group, let's see. One example is like S5 times Z2, okay? It can have two different representations, which are both 5-dimensional. If you start by thinking, okay, let me analyze all the Landau series with this group, I might think that I need to write two Landau series for each of these representations.
Yeah, that's what I mean.
Yes. So what I was trying to explain is that because of this automorphism, these two ways of writing down the Landau theory would be related, would be equivalent. That these two Landau theory would be related to each other by some field redefinition. So, in other words, given a symmetry group and how many Landau theory you can write down, the answer should be the representations mode out automorphism.
I understand on this,
yeah,
but if they're not related by an automorphism, then that means
then
that you
there
have
would
the
be
same
two
symmetry with different order parameters.
Exactly.
Okay.
Yeah, thank you very much. So we did this work. We have a list of groups, a directed graph of groups. And remember, I said there's another thing you can check, which is called the Landau conditions. In this case, you check something called Mollin series, which is something defined as, sorry. Okay. This is the order of the group. This is all the group elements. This is the representation of the group, which is now a matrix. You use identity minus this matrix. Sorry, I forgot one parameter here, which is the auxiliary parameter, which we call T. And you calculate this. This is called Morning series. And it counts for you the number of invariant polynomials. So what you are going to get is something 1 plus some number T, number T squared, number T to the third. This is related to irreducibility. Yeah, this is the Landau condition. Luckily for all these groups, you can easily calculate the Morning series with one command, and you can check these Landau conditions easily. So in the end, we have a directed graph. We have many, many groups. They are related by group-subgroup relations. We look for the one that respects Landau conditions, but also the lowest one. So after that, we are left with two series to consider. The first group you need to consider is something like it may look abstract, but let me write down what are the polynomials. The first polynomial is basically phi 1 squared plus phi 2 squared, phi 5 squared. Okay. I mean, you can already imagine what this group is. This is the one isotropic one. This group breaks, this polynomial breaks the isotropic ON into the cubic group that Stefanos mentioned in his last talk. And this group, this one further break the cubic group into this group, basically. I don't think I need to explain how this group acts, but you can kind of imagine from it. Sorry, can you? No, this is not naively cube symmetric because you didn't have things like phi 1 square, phi 4 square. This is not. This is cyclic. Yeah, it's only cyclic. So it's a smaller group than the cubic term. So you parameterize your potential in this form. You plug in that equation. You got many, many fixed points. And in the end, you got 4 real fixed points. I will call this one lambda 1, lambda 2, lambda 3. You got F1, which is lambda 1 equal to lambda 2 equal to lambda 3 equal to 0. This is the free series. You got F2, which is equal to lambda 1 not equal to 0, lambda 2 not equal to 0. Well, lambda 2 equal to 0, lambda 3 equal to 0, which is the Euro 05 fixed point. You got F3, which is lambda 1 equal to 0, lambda 2 not equal to 0, lambda 3 equal to 0. This is decoupled cubic. F4, which is lambda 1 not equal to 0, lambda 2 also not equal to 0, lambda 3 equal to 0. This is a cubic file. Okay. In fact, I mean, we have like 3 unknown variables, and we have a degree 2 polynomial. We are supposed to find 8 solutions. So besides these 4, we have another 4. Fixed points. Okay, everything works nicely. And the second one is the S6 times Z2 series that Stefanos mentioned very briefly in his talk. The first polynomial is this P1, which is the same as this one. The second polynomial is this one, P2. You should write it in this way. Okay. And this E alpha I, alpha runs from 1 to n plus 1. And this I indices runs from 1 to n. So it tells you how a hypertetrahedron is embedded into, a hypertetrahedron with n plus 1 indices is embedded into n-dimensional space, Euclidean space. So for example, when n is equal to 2, so you have a hypertetrahedron which is with 3 indices, which is a triangle, vertices, triangle. So it basically looks like this. Well, it's E1, E2, E3, stuff like that. There's a recursive way to start from this to build the higher dimensional hypertetrahedrons. So after running this one, you find, again, some fixed points. You, of course, also find the free one. You find another one with lambda 1 equal to 0, not equal to 0, lambda 2 equal to 0. This is, again, the O5. You find it again. So as promised, I'm looking at the smaller symmetry. I should be able to find all the fixed ones with higher symmetry. And the third one you find, there is a fixed point with lambda 1 equal to 2 pi epsilon square. Lambda 2 equal to 25 pi square or 9 epsilon. And you only find 3. So as I mentioned, we need to find 4 because 2 to the factor of 2 should be equal to 4. So there's some of them has to have degeneracy. In fact, this one has degeneracy. If you push it to second loop, you realize that there are some second loop result. So you can see, at leading order, it looks innocent as a real fixed point, but at second order, they become complex. So the power also gets changed. So
this is the known hypertetrahedral fixed point, right?
This is the known hypertetrahedron fixed point. So that's what I'm going to comment right now. So this hypertetrahedron fixed point, you can construct it for arbitrary n. So you do it for n plus 1. So it just happens that at any n not equal to 5, you would find a pair of real fixed points. At exactly n equal to 5, you find a pair of complex fixed points. So you should ask what's happening. So when this n is approaching 5, when n minus 5 is a small parameter, you shouldn't trust your perturbative expansion anymore. You shouldn't, because there's competition between epsilon and this small parameter. So when this small parameter is actually small, you shouldn't trust your exponent expansion. So we don't really know what's happening there. But most likely what's happening is that at large n, you have a pair. As they approach n equal to 5, See, collide and go to complex plane.
What do you mean? Yeah, we know that's happening.
We know that? Well,
Yeah.
Yeah, we know that, indeed. In the original papers of Zai and other, they already know it.
Yeah.
But
They just collide for n equals 5 at leading order in the epsilon expansion, that's all.
yes, but again, as you lower, yes, let me finish my comment. So let me go, as you go to even lower n, because when n is equal to 3, this group is isomorphic to the cubic fixed point. So therefore, it must come back to some n, come back to the real plane again. So really what's happening is that they collide, go to complex plane, and then come back. This has been known for a while, as Andy already mentioned. But maybe it's interesting to see at exactly which end this happens. So, yeah.
Position of this n receives corrections order by order in epsilon. So you mean maybe with a bootstrap to see exactly what?
Yes. So I mean, I think I will use my last minute to comment on the bootstrap. So, I mean, you can set up a bootstrap system for this theory at large n, even at single correlator. One of these channels, you see that the curve, the gap maximization curve, approaching the Eason curve from below. So at infinite n, you expect that this theory goes back to the spectrum of the Eason model. So in the early days, 2017, with Ning, we tried to do this system. And so what's happening really is what I just mentioned. So at large n, there's a curve which is starting to approach the Eason bond. So I would interpret that as a signature of this fixed point at large n. But of course, now we have much sophisticated numerical techniques. It might be interesting to retry this. And okay, let me add one last comment about what else we can do. Of course, we restrict ourselves to like one relevant operators in the system. You can relax this condition and see, okay, I don't want to only care about one relevant operator. I also care about three critical phenomena. So I can, again, look at this list of groups and look for like maybe two representations which add up equal to 5 or equal to n. So to study the corresponding Landau theory. So you can, I'm sure you can finish that. And there's a, basically in format epsilon expansion, renormalizable series are limited, right? We have the gauge coupling, we have the Iwakawa coupling, and we have the scalar lambda phi 4 coupling. So you can even generalize this to study this most general renormalizable theory in format epsilon expansion. And with the help of group theory knowledge, you can see more about it, be systematic, even though that, as we did here, the number of views might be limited. So the last comment is up to when should we stop, right? So this sounds like an infinite game. I mean, there n can be 5, 6, 7, 8, 9, 10, whatever. So I think, okay, one way maybe we stop is that we have a good understanding of our reducible fixed points for higher n. So suppose magically we are able to solve it, we will stop. But I want to also argue that physically, maybe the low number of scalars are the most interesting ones. So, but the cutoff, we don't know how physical system might surprise us or not. But we have one data point, which is the representations, which is structure phase transition. So there is this special type of transitions, which there's crystal, that the crystal changes structure as you lower temperature. There are some phase transition between high temperature phase and low temperature phase. And in that case, the Landau theory is basically described as the representation theory of the space group. So the representation theory of the space group is known. So people has classified it. And in that case, the Landau theories that people are getting, I think they get scalars up to 26. I think that's, so even though in that case, we don't really find a stable fixed point there. So this is just to give you an estimation about what are the interesting set of, what's the upper bound on n. Go ahead. 24, sorry. 24 scalars, if I remember correctly. Yeah. All right, that's all.
Okay, with time for questions and comments as well.
So here you have some equations up to quadratic order in lambda.
Yeah.
You could also add the cubic term in lambda. Are there any new solutions if you keep the terms up to cubic order that you can't see?
Well, but we
Yeah.
want to. Okay, basically, what's happening is that we want this coupling to approach 0 as you go to 0.
Right.
So basically, the solution you are going to find at first order gets corrected at second order. But if you naively add that third term, even though if you find solutions, it's possible. If you set epsilon equal to 1, you find solutions, but those solutions would not go back to 0 as you.
Is it clear?
I mean, you.
So this quadratic term has some positivity properties, or the quadratic
No, it's
lambda
just
term?
well. It's Mike. It's
Right.
somewhere. Yeah.
Well, if you, okay, yeah, maybe we can talk about it.
I think nobody heard what you said, Andy, but okay.
You have a comment?
So I can comment on Silvia's question. So it's a theorem that if you are at one loop, you count how many solutions you have. If all solutions are non-degenerate, which is easy to check, then you know that by going to the next order, all solutions are just going to be corrected and you're not going to find any new solutions. If some solutions are degenerate, then in fact, at the next order, they can split, like for example, it happened here, and you have to go to sufficiently high order until all the solutions split and all of them become non-degenerate, and then you have to stop. So that's a simple theorem to prove about formal power series.
This four complex fixed points that you mentioned, which symmetry do they have?
They have this one, this
Just that
smaller
one.
symmetry, which, I mean, all three couplings are turned down, basically.
And it could be that as I move, for example, in dimension, they go back to being real fixed point or something
Yeah,
like this. That would be a scenario. Is there any sort of reason to believe that they might be interested in fixed point at d equal 3, or we should not care about them?
I think in general we should care. I mean, we should, in principle, do higher loops and try to see whether, whether they become real. There's any tendency that they become real again or not. I want to comment by saying that even if it is not, it is complex. If the coupling is complex and small, it may still affect the RG flow and may still be physically interesting. Yeah.
Okay, thank you.
Just a comment. In my work with Hugh Osborne, we showed basically that, well, with an extensive numerical search, which isn't a proof of anything, but suggests that the reducibility condition has to be relaxed if you want to find new fixed points. And
This is similar to what we are finding here, right? In Get 5.
yeah.
Yeah.
So, but we have, tables of fixed points if you relax the reducibility conditions that are biconical, triconical of this type. And the comment is that the way to generate new fixed points at higher n, except for sporadic cases perhaps, is to recycle in this biconical or multiconical way fixed points that you have at lower n. And that could be something that can be proved. Of course, we haven't proved it, but it would be great if someone could prove such a thing.
Yeah.
The numerical results suggest that it's true.
So you're basically saying that the biconical way is
It can be multi-conic. It could be,
yeah, it would be really nice to
so
have
the sort
a
of like
proof
double trace perturbations of decoupled theories yield fixed points at larger n, and they seem to be the only way to get fixed points.
I see. I see. Thank you.
More comments, questions? Okay, if not, let's thank Jun Chen again.